Ladies and gentlemen, welcome to our session on HIP for nuclear applications. You might be somewhat intrigued by our title slide. All will be revealed. Roughly halfway through the presentation, you will understand why we want to talk about chocolate and diamonds. So my name is Heidi Lovelock from DELORO Wear Solutions. My colleague, Alle Snyder, will be co-presenting with me today. And what we're going to cover is, firstly, just a brief review of the limits of the classical production methods that are used, such as welding and casting, and then why hot isostatic pressing is a potential alternative solution to those issues. Some of the key success factors to bear in mind when we want to use hot isostatic pressing. We'll then take a brief look at some of the powders that DELORO offers for hipping and compare finally with a bit more data, having understood the process better, when is HIP appropriate compared to perhaps some of the other manufacturing processes. So now I'm going to hand over to my colleague Anna to talk about the limits of the classical manufacturing methods. Thank you.
Merci. Bonjour à tous. I will switch over into English. A little bit higher, is it better? Okay. So the limit of the classical manufacturing methods. All the four pictures here shows processes we have at DELORO. All are fine, we use them every day. However, in some critical applications, we might need some enhanced properties in terms of mechanical properties, in terms of corrosion resistance. In order to avoid certain kind of defects which are not accepted in the aircraft industry, for example, in the pharma or in the nuclear applications. Also in the cladding manufacturing, we have at DELORO some welding application like PTA welding, TIG or oxyacetylene. We also use laser cladding. We offer also PTA solutions, which are able to weld in internal diameters, in very small diameters as well. However, here we are facing also some challenges. For example, if we need to go in a very small diameter, in a deep bore, with the cladding we are facing thermal cycles, residual stresses, distortion, some special torches we have in our portfolio needs some very special training to use them. And sometimes we have also some bores which are much smaller than 25 millimeters and very deep in the material. Also, the hard facing, the cladding, affects the hardness and the corrosion, as you can see here on this graphic. The black line is for TIG welding. The white is for PTA, plasma transfer arc. So you see how the dilution affects the hardness, but also the corrosion resistance. What can we say about additive manufacturing, which is another family of manufacturing processes? In the five past years, we had quite a collaboration with some external institute to develop additive manufacturing with stellite alloys, which are cobalt-based alloy, tribe alloys as well. We found that laser powder bed fusion, LPBF, might represent many challenges in terms of achieving parts with a high density, etc. Okay. And the machines on the laser additive manufacturing requires also a higher temperature to preheat the alloys we are serving. And the machines are currently practically not available on the market. We believe in binder jetting. It's a promising alternative to the process we have seen before. The binder jetting is also a powder-metallurgical process where sintering the parts can be an additional step to make the part more dense and reduce the porosities. So this is an hipping process to make the part denser. At that point, I will hand over back to Heidi, who will present the HIP process in more details.
Thank you, Alain. Yeah, so now we've understood that although casting, welding, and additive manufacturing processes they're great processes. We know them well, we use them every day, and they're good for most applications. But there are some challenges, and especially for demanding applications like nuclear applications, hipping is a good alternative. Firstly, what is hipping? Just for those who perhaps aren't that familiar with it. Effectively, if you look at the diagram on the right, what we have is a very high temperature furnace inside a pressure vessel with argon, or normally argon gas, circulating through that vessel. So this is not just a pressure vessel, it's a pressure vessel at about 1,200 degrees C. So that is quite a, complex piece of equipment. The parts that are inside this furnace are treated at very high pressures. You can see on the slide, very high temperatures, and usually in argon. And what's important to understand is, the key is in the name, hot isostatic pressing, is that the gas presses onto the component from all directions, isostatically. This is a diagram, a schematic of a HIP plant. Now, the key thing to notice here is that, in fact, more than half of this plant is below floor level. If you look at the diagram carefully, you'll see where the floor level is. And that's mostly for safety reasons, also for space reasons. There is a photograph of a HIP plant. This is just the part that's protruding above the floor level, just so that you can get an idea of what they look like. Now, most HIP cycles involve a very slow cooling after HIP. So this is shown schematically on the right by the dotted line. You can see that conventional HIP cycles, the red dotted line shows you the temperature, the blue dotted line shows you the pressure. So effectively, you're ramping up at the beginning pressure and temperature. You're then holding it at high pressure and temperature. This is the actual HIP process itself. On that horizontal line, typically around 4 hours. And then there's a very slow furnace cool, usually. Sometimes there's a faster cool up to about 900, down to about 900, followed by quite a slow, what we would call a furnace cool in most of metallurgical world. However, some HIP systems do feature rapid cooling, and that can be really helpful. That's shown by the solid lines there. That can be really helpful if whatever you're hipping doesn't tolerate slow cooling for whatever reason, or cannot be post-HIP heat treated to restore metallurgical properties. So the most common application for hipping, and probably the application that everybody thinks about when they hear hipping, is for the densification of cast components. And we have a picture here of a HIP implant, because quite often HIP implants are hipped to reduce the porosity of the casting. What's really interesting, of course, is that these are investment cast components, and investment casting is the best casting method that there is, produces the best quality. Nevertheless, because really good fatigue properties are needed, they're still post-hipped after casting to reduce the internal porosity. Similarly, sintered powder, metallurgical produced parts, MIM parts, PIM parts, are also hipped to reduce porosity. And as we already mentioned, we're going to be looking at hipping to post-treat binder-jetted AM parts. That's just a schematic of how that works before and after hip. What happens effectively is that the very high pressures, the very high temperatures in the hip process obviously cause the pores to collapse under that force of the pressure, but also the temperature allows the gases inside the pores, if there are any gases, to diffuse out to the surface. Here's an example of metal injection molded turbine blades loaded into a hip furnace, being hipped. Again, these are vacuum investment cast parts. Nevertheless, they still require post-hip heat treatment to really, well, it's not the heat treatment, it's the hipping to remove the porosity. There are a couple of important graphs on this slide and the next graph, and in the interest of time, I don't want to spend too much time on them. However, the key message here is that in particular, toughness and fatigue life are absolutely dramatically dependent on porosity. And here you can see the cycles to failure on the x-axis, the applied stress on the y-axis. The bottom set of curves with the open circles is unhipped. It's the same alloy, it's a die-cast aluminum alloy, and the solid triangles on the top line are with hip. Now that doesn't look like an awful lot of difference, does it? But actually the fatigue limit, which is the value at the very right-hand side at an infinite number of fatigue cycles, is what counts, and it's been improved by 43% through the application of hipping. These graphs come from the ASM handbook. Similarly, the graph circled on the right shows you just how exponentially toughness depends on porosity. So you have the percentage porosity on the x-axis, you have the impact resistance on the y-axis, and as the porosity goes down to even just 2 or 3%, you have a massive decrease in the toughness of the component. So that's the densification of cast or PM parts. The other excellent application of hipping is making solid parts from powders. And that's great because as long as you can make a powder, you can potentially, at least in theory, make a component or a bar or a solid out of that powder. And what does that mean? It means you can mix different powders, you can create alloys that you could never cast, that you could never make in any other way. How does that work? Effectively, as you can see on the bottom here, you have typically a mild steel can, which is filled with the powder, closed. All of the gas is evacuated out of that can. It is then subject to hipping, and the capsule or the can is removed afterwards. And then you have, in this case, a solid block of some new material. But of course, you can also make the can a certain shape so that you can get a near-net shape component. Here's an example of a near-net shape component. So if you make the can, the geometry of the can, you need to spend quite a lot of time designing that because you need to think about shrinkage and distortion. But if you get that right, then you can actually produce a hipped component from powder that is near net shape. And now we get to particularly the DELORO alloys. And what is fascinating about a hipped component versus a cast component. Now this here, on the left, is a stellite 20. It's one of our alloys. It's a cobalt, chrome, tungsten alloy with a very high carbon content, a very high carbide content. That is a cast alloy on the left. And if you look at it, you'll see that you have a light gray cobalt chrome matrix. You could imagine that that's a ductile matrix. You have dark gray chrome-rich carbides, big blocky things which actually go into the picture. They're actually a spiny shape. And then you have white carbides, which are tungsten-rich carbides. But if you look at the shape of those carbides, and if you imagine a crack potentially traveling through this microstructure, it's basically, it's not a very ductile microstructure. It's not a very tough microstructure. It's extremely wear resistant, but it is not ductile. However, if you take exactly the same alloy in powder form and you hip that powder, you get a completely different microstructure. The carbides are homogeneous, they're rounded, they're small. So a crack cannot travel through this microstructure as easily. It is much tougher. And I've got some data here from a paper that I did, some research that I did about 15 years ago, which just tells you that the fracture toughness of the hipped microstructure of the same alloy is 6.8 times better than the cast alloy. That the rolling contact fatigue, which is very dependent upon fracture toughness, is actually 200 times better. This was independently tested by a university laboratory. You have the composition of the alloy at the bottom left. And here's already a little clue as to our title page. You can see that we're comparing the hip microstructure to a diamond because it has a homogeneous, consistent structure. Whereas, if you think about that cast microstructure that we just saw 2 slides ago with those big carbides, that is a little bit more like the carbides being the nuts in the softer chocolate cobalt chrome alloy matrix. So now you also know that we're halfway through this presentation, slightly over halfway. Right, and then finally, a fascinating application for HIP, which we've been working with a lot lately at DELORO Wear Solutions, is using HIP to bond a hard wear-resistant alloy or a corrosion-resistant alloy to perhaps a steel body or a steel component. And you can bond powder to powder, you can bond powder to solid, you can bond solid to solid, which is really just diffusion bonding, actually. Why would we want to do this? Well, if you have, for example, an internal diameter that's really deep and really narrow, you can't do that by welding. You can't apply your hard facing by welding, for example. You also can't make it necessarily by casting it because it's a bimetallic structure. So the answer is to actually use HIP to apply the second alloy as a powder into the inside of the body, steel body, for example. Here are some examples of HIP bimetallic parts. On the left, you see hard facing on a roll. Of course, you can do that by welding, but there are other metallurgical reasons why you might not want to, why HIP would be a better idea. Property reasons, mechanical property and fatigue reasons. In the middle, we have some bimetallic valve plugs that were made using hipping. And on the right, you can see an extruder housing where we have a HIP PM stellite hard facing on the inside. So in summary, the quality benefits of HIP PM, not the cladding, but just the HIP PM where one makes a component from a powder, are that the component quality and performance are much better. So you have this homogeneous microstructure, you have a very low porosity and very small pores, which is absolutely crucial for fatigue and toughness. And there's also no alloying element segregation, which is the kind of thing you get mainly with casting, but also with welding. There are design advantages. We can make near-net shapes, we can make bimetallic constructions. There's a lot of design freedom once we bring HIP into the equation. We can make mixtures of powders, we can invent new materials, actually. There's a freedom also of part sizes and production series size, because most HIP subcontractors are running a certain HIP cycle every day of the week, and the components go into the furnace and they get hipped. So there's a lot more flexibility there. And I think I already mentioned the last point. There may even be cost advantages. Even though hipping is expensive, there can be really cost advantages in some cases where something that used to be made of several components and having to be welded together and joined together, and all of that inspection and all of those weld procedure qualifications are gone, and you just make one part using hipping. You can reduce the number of welds, and you can also reduce the machining needs if you use near-net shape HIP. So, of course, as with anything that looks simple, it isn't necessarily. What are the key success factors? There are many. I just picked two. The capsule design, the capsule manufacture, the consideration about how will the part shrink or how will it distort is not simple at all. And the powder specification is also important. Of course the hip cycle is important, of course other things are important, but we only have 30 minutes. So the capsule design is important because the capsule has to be gas tight. It holds the powder in place during the hip process. It gives the powder-based element, particularly in bimetallic hip, its final consolidated shape, and it's removed after hipping. Here you can see a little schematic of how a capsule is filled under vibration, vacuum degassed, closed, hipped. You can also see schematically the distortion represented there, and then the final machining to get your final part. The other big success factor is powder. The purity is important because surface oxides and other impurities don't disappear. When you hip a powder, those prior particle boundaries are still there. Those oxides don't go away necessarily. So purity is very important. Shape is important. Generally, provided it's possible, a spherical powder is preferred because of the packing density of a spherical powder is generally better. And the particle size distribution is also important so that the powder, the tap density of the powder is as high as possible so that we can get as low as possible shrinkage and distortion. Therefore, because of all of these reasons, gas atomizing, which is shown schematically on the right, is actually the preferred process for hip powders, particularly for metals and alloys, basically provided one can gas atomize the material that we're hipping, of course. And what's important to know is that we have 3 gas atomizing plants within the DELORO family of companies. We have one in the US, we have one in the UK, we have one in Germany. So we make our own powder effectively in-house within our family of companies. In terms of analysis methods, you need to be able to analyze what you've got. We have a powder analysis laboratory, we have a metallographic laboratory, we have many NDT processes. I'm not going to read those out. And we offer, as I already mentioned, hip powders. I'm going to present a very small selection of powders here, just to give you a flavor, but we have hundreds of powders, so please speak to us if you need to buy any powders for hipping or indeed for any other application. These are our typical well-known stellite alloys. We've arranged them from top to bottom in order of hardness, and the basic trend is that the more carbon and the more alloying elements they contain, the harder they are and the higher their hot hardness is as well. At the bottom you can see stellite 20. That's the one we used for the example earlier, the hardest and the most brittle one. We also offer nickel-based powders. I just listed the 3 most commonly known ones here, the DELORO ones. Again, different hardnesses, different hard phases. And then we have iron-based powders, which is particularly interesting for nuclear, of course. The NORM2, which is very well known. And then antinet 300 and 500 are some examples of powders that can be purchased from us for hipping or for hard facing. So just in summary then, when is HIP an appropriate manufacturing process? When quality and performance is critical. That's the bottom line, actually. Aerospace, medical implants, nuclear parts. Where you need not just better mechanical properties, but more reliable and consistent as well. And where design flexibility is needed, we already discussed that. Where perhaps the conventional manufacturing costs, all of the inspection and welding is becoming just no longer realistic to bear. And when is bimetal HIP appropriate? When the geometry is not feasible for welding or casting. That would be the first clear application. If you can't apply a weld hard facing, you can't make a casting, then HIP bimetal is obviously the way to go. Or when the properties from an as-cast or an as-welded microstructure are simply not adequate. Or when dilution from a weld overlay is unacceptable. I've done a short comparison table here. This is the last slide. Just comparing very briefly the different properties, welding, casting, and hipping. I'm going to leave that there for a while. Just take a look at that. We have a more detailed version of that, a paper version, on our booth 68. So please come and visit us. And if you have questions and answers, we're next door. Thank you very much for listening.